I thought nothing, no song could possibly be better for our whirlwind tour of radicals than Anarchy. A little morning dose of the Sex Pistols, right? Good stuff. All right, I did get pie on Wednesday. It was stickier, honestly, than I thought it would be after a while. So I recommend you eat pie, actually, and not flavor it. Yeah, really. All right, so here's my goal for the day. We've got to cover radicals, and I want to do it and not think about it past this weekend. So we're going to try to do that. And honestly, I think I'm going to leave out a lot of details, because I don't think they're that important. I don't think that they're that important to you. And in fact, we might have a few minutes to actually go over some funner aspects of radicals. So I feel like things have been pretty information dense recently, so I tried to think of maybe a few actual radical applications, and we can talk about that. All right, so let's, I have no idea where we left off. Let's see. I should do this before class, maybe. All right, so we left off at radical stability. We talked about how it's pretty much the same as carbocation stability, right? So some tertiary is more stable than secondary, which is more stable than methyl, etc. So I'm gonna actually, let's copy this over. We'll go off of this. All right, so we've got some stabilities here we talked about. I did it. Oh, okay. Forget it. So, let's see. Knowing what we know about the stability of these radicals, we can actually start thinking about maybe some bond strength. And so to consider some CH bonds, let's take a look. So let's say we have this molecule. What we'll do is we'll compare it to just methane. All right? And so what we want to do is we want to compare the CH bond strength. That's not methane. This is methane. What we want to do is compare the bond strength of this CH bond versus this CH bond. Really, we could pick any of the CH bonds of methane, but it'd be the same. All right, and so knowing what you know about the stability of radicals, and so that's the product, of course, of a homolytic cleavage. What do you think's the stronger bond? Is it going to be the CH on the left or the CH on the right? Well, which product is easier to form? Is it going to be the product of homolytic cleavage of this compound, or is it going to be the product of homolytic cleavage of this compound? Certainly this product is more stable, right? And just like when we talked about acids, right? Acids are stronger because their bases are stable. It's the same thing here. Okay, so when we talk about bond strength, we can say that this bond is going to be about 381 kilojoules per mole. And so on the right side, we're going to have a bond that's about 435 kilojoules per mole. And so that goes hand in hand with our radical stability. So this is not going to be a very stable radical. In fact, it's not even a radical at all yet. Now it's a radical. And so that's going to be our least stable radical. And because it's so unstable, it's going to be difficult to form. And so that actually makes this CH bond very strong, because this is a lot more stable than that. The difference in energy is less so over here, right? Because we know that this is a very, very stable radical, and because of that, it's just going to be easier to break that CH bond. And since it's easier to break that CH bond, we end up with a weaker bond on the left side. So that's going to have some implications when we talk about regioselectivity of our reactions. All right, so we've talked about substitution. We can also compare a few other radicals. So let's see. We can compare this radical to, sorry, I should actually draw a radical, to this radical. And we'll also, again, go back and compare this to our tertiary radical right here. So what do you think is the most stable radical? If we're treating this thing like a carbocation, what would be the most stable carbocation if we had a plus charge instead of the dot? All right, so could we draw some resonance structures? Yes. Yeah, we absolutely could. And so in the structure on the left, we could actually end up showing that positive charge at 4 different locations, right? We can draw a lot of different resonance structures because we can resonate that charge around the ring. Just like we can resonate a charge around the ring, we can also resonate a radical around the ring. But do we want to use full arrows? No, because when we're moving radicals around, we're moving single electrons. So what kind of arrows do we use?
Fish hooks.
We use fish hooks. And so to show a resonance structure that could result from this radical, we start with this electron and show a fish hook. And then here we're going to break this bond, but again, we're just going to break one of the electrons that way, which means that the other electron is going to pop over and end up as the radical electron on this benzene carbon. And so what we end up with is this radical right here. Okay, and so of course, there are going to be 2 more resonance structures that I can let you draw out for practice. But basically, we're going to be able to put that radical both at this position as well as this position. So there's lots of possible resonance structures for the radical. And knowing what we know about resonance and stability, is that going to make for a very stable radical or a very unstable radical? Very stable radical, right? So what we'll have is over here, the most stable. And as we work our way across, we're going to end up with the least stable of these 3. Okay, so of course we can draw a resonance structure. So this is going to be a special type of radical that we refer to as an allylic radical. And so basically an allylic radical is going to be some radical that's next to an alkene. And so it's a really special radical because we know that it is resonance stabilized by that alkene. And so we can show that resonance structure just like that. So ultimately we have a radical that really is kind of at 2 positions at once, just like we think about a carbocation having positive charge at different positions. We have radical-like positions at different carbons on this structure. All right, so just like substitution is common between carbocations and radicals, so is resonance and the stabilization therein of those structures. All right, so if we think about the CH bond strength in this case, let's take a look. So to form our radical above, we would undergo homolytic cleavage of this, or at least one of these CH bonds. And then for the allyl radical, we would undergo cleavage of these CH bonds, and then of course we've already seen that to form the tertiary radical, we undergo homolytic cleavage of that CH bond. All right, so just from above, we saw that the CH bond strength down here is about 381 kilojoules per mole. And so knowing that we've got even more stable radicals on the left side here, do you think that the CH bond strength is going to be stronger or weaker? Weaker, right? It's going to be easier to undergo homolytic cleavage because we're going to end up with really, really, really stable radicals. And so what we see is a CH bond strength here of 364 kilojoules per mole. And then in the case of the benzene ring, where we have lots of different resonance structures, so this radical is really spread out, we'll end up seeing a bond strength of about 356 kilojoules per mole. And like I said, this is going to matter a lot when we start talking about the regioselectivity of our reactions. It's going to help us determine where a reaction is going to take place. Yeah?
So the less stable the radical is, the more stable the completed.
Yeah, if we have if a homolytic cleavage would result in a very unstable product, that means it's going to be a hard process to undergo, right? Because the product is so uphill. And so because it's so uphill, that means that the CH bond over here that's going to be relatively stable, it's going to be hard to break just because it takes a lot of energy to go way uphill and form an unstable radical. All right. So when we look onto a molecule, we can say, for example, we want to identify the weakest CH bond. So for our molecule, we're going to say, we'll make it sort of complex. It'll look something like this. Okay, and so what we're going to learn is that we're going to react. We're going to undergo some reaction at one of these CH bonds. And so the weakest bond is going to help us, or picking out the weakest bond will help us determine where that will be. And so of all these carbons, what do you think is going to be the weakest CH, or at least have the weakest CH bond? Yeah, so let's take a look. So we've got primary carbons. Those are going to be very weak. Here we've got a tertiary carbon, right? And so that's a pretty good candidate for being the weakest CH bond. So we'll go ahead and draw that in. Do we have any CH bonds here? No, that's a quaternary carbon, and so even though theoretically it might be stable because there's more substitution, there's no CH bond to break, and so we can't consider it. So then let's see what else we have. We have a secondary CH bond right here that we can consider. And I do want to add that sp2 CH bonds are very strong. And so because they're very strong, we don't consider the CH bonds involved in that alkene there. So we can just, if you see an sp2 hybridized carbon or an sp hybridized carbon, you can pretty much not worry too much about it. All right, so really we're looking at a secondary versus a tertiary. So which would be we expect to be the most stable? Tertiary. All right, but that's secondary. That's a special case because it's next to an alkene. And so what do we call a radical that can form next to an alkene? It's an allylic radical, and we've seen that that's actually more stable. And so what we would expect is, since here we would be able to form an allylic radical, this would be our weakest CH bond. And so it's going to be important that we be able to kind of look at our structure, think about the radicals that can form, and then determine which would be the most stable radical. And it really is just like thinking about carbocations. We're looking for substitution, and then we're also looking for resonance, and resonance is pretty much always going to trump substitution. So we're going to do 3 reactions, and that'll kick us off into the first one. So Roman numeral number 2 we will call the radical halogenation of alkanes. All right, so in the radical halogen, this is actually pretty neat because we've always kind of, when we've talked about alkanes, we've said that they're not very reactive other than we can set them ablaze and use their heat. So it's not totally true because we can take something like methane and we can react it with, say, Cl2. And with just Cl2, nothing's going to happen. But if we also add in some of this stuff, what is this? So this is basically, this might be an introduction to chemical shorthand. This is chemist's abbreviation for light, and often ultraviolet light. So we can't just treat this with Cl2. Often what you'll do is you'll put like an ultraviolet lamp next to your reaction because nothing's going to happen without the light. It's just a necessity. And honestly, it's a little beyond Chem 206 to know why that is. But if you're a chemistry major, you'll learn about it. You'll know why it is that way. So just for now, know that we have to have light for this reaction to proceed. And so what we end up seeing is more or less one of our hydrogens has been replaced with, what do you think?
A radical.
Yeah.
We'll see that there's a radical involved. In this case, we just want to show the product. And what we've done is we've made chloromethane, which that's kind of neat because this is the first time we've ever actually reacted an alkane, right, with a CH bond. So, and in reality, CH, that's a big field in chemistry, is determining how we can continue to make CH bonds more reactive because they're typically not. All right, so let's talk about mechanistically what's going on. So this is our first look at a radical type mechanism. And so we call a radical type mechanism a radical chain mechanism. And so what we'll find is there's 3 steps. There's basically the generation of a radical, and then there's the middle step where pretty much all of our actual reaction we're interested in goes on. And then there's the last step, which is termination. And so the beginning and the end, the bookends, they don't happen much. All the good stuff sort of happens in the middle, and we'll see why that is. So step 1 in a radical chain mechanism is going to be initiation. And so initiation is saying it's an initiation of radicals. So what happens in our initiation step is we're going to have chlorine. So we actually don't start with our alkane. We're going to start with our chlorine. And so really it's our chlorine that's being subjected to the light, and when that occurs, we undergo an initiation step where basically this sigma bond undergoes homolytic cleavage and splits in two. And so what we really end up with then is going to be two Cl radicals that look just like this. All right, so not a lot of this has to happen because once we have a radical generated, this radical can have a pretty long-term effect on things. And so we'll see why that is in our next step, which is propagation. I think propagation is with an O. Irvin, what do you think, A or O?
I think it's O. A?
Yeah, here, consensus on A. All right, look that word up, please. All right, so propagation. And so this is where the action is. This is where our fun organic chemistry reaction stuff's going on. And so what happens is once we have our Cl radical is going to react with our methane. And so we'll just say we have methane, and we're just going to draw it out like this. So we're showing that one of these CH bonds, in reality they're all reactive, but we're just going to focus on the one that's reacting. And so what we have is a combination of our methane and our newly generated Cl radical. And so the reaction that's going to take place from here is we're going to draw fish hooks just like this. And so ultimately what's going to happen is one of our byproducts is going to be what? Yeah, we're going to form HCl. But in the process, we're also going to draw a fish hook back to this carbon. And so what we end up with is our radical right here. So more or less what we've done is we've transferred our radical from that chlorine over to the carbon by undergoing cleavage of the CH bond. And so from here what will happen is we have our methyl radical. And you know, we've generated multiple chlorine radicals, and so we'll have another one that we can play around with a little. And so we kind of know, we know what we're trying to get to, and actually, back that up, we're not going to react that with the chlorine radical, we're actually just going to react that with the chlorine that we have in our reaction. So there's tons of that. So as soon as we generate our methyl radical, that's going to probably run into some of this chlorine. And so what we end up with is then drawing new fish hooks. And again, we want to make sure we start from our sigma bond. And so in effect, our propagation step is going to be a two-stepper. We've added a chlorine to our methyl group. And so what else have we regenerated? That same chlorine radical that we initially had formed in our initiation step. And so that's why, in reality, not a lot of that initiation step has to go on, because every time we undergo our propagation cycle, we're going to regenerate our chlorine radical, which gets to dance all the way back up to the top, right back to there, and undergo another reaction with a new molecule of methane. And so in reality, in our reaction, the concentration of radicals is low. We really don't do a ton of initiation, but once we've got one of those chlorine radicals, it can pretty much undergo this cycle with lots and lots and lots and lots of different different numbers of methane molecules. And so it's very much a chain, right? We're kind of looping back. We go here, here, and then right back to the beginning. And so it's sort of like a cycle that we're looping back around on. All right, so of course we don't last forever. Nothing lasts forever. And so then we get to step 3. And so step 3 is our termination step. And so this is ultimately going to destroy radicals. And so this doesn't happen a lot because we never actually have a ton of radicals in our reaction at one time. But every now and then some radicals are going to bump into each other and we can undergo a radical-radical interaction. So for example, we could have a chlorine radical that runs into another chlorine radical, and so when that happens, we're going to destroy our radicals and reform our chlorine just like this. There's lots of honestly different possibilities that occur. So we could also have, say, a methyl radical that runs back into our chlorine radical, and so that happens. And so that actually leads us to the product that we're trying to obtain in the first place, but this isn't typically how that product will form. This is only going to form this way when we're in a termination step. We can also have a methyl radical run into a methyl radical. And so really what we've got to consider is all the possible radicals that we've generated in our molecule. So in this case, we've actually created ethane, which is not really the goal. But are we going to create a lot of ethane? No, we're not going to create a lot of ethane because this termination step doesn't happen much. And so when we think about the products of our radical chain mechanism, it's going to be the products that we form up here during our propagation step. It's just we need to be cognizant of the fact that as our reaction comes to completion, we're going to have radicals that no longer can react with anything useful, and so eventually they're going to bump into each other, and pretty much they're going to all go kaboom and form these other molecules. But these never form really in any substantial amounts because the termination step doesn't happen too much. All right, so we've got a three-step mechanism and a radical chain. We have initiation of our radical, propagation where the meat and potatoes is, and then termination where we destroy our radicals. All right, how are we doing on time? 10:21. We're doing okay. Let's see. This is where we're going to have to probably cut some stuff. And so next, we just want to talk briefly about the thermodynamics of these. And honestly, some of this stuff is really interesting, but we've got a lot more interesting stuff coming next week that we really want to get to. And so something's got to go. And so we might ask ourselves, which halogens can do this? And so what we find is in terms of reactivity, we work our way down the periodic table. So the more reactive stuff is on the left side, and the less reactive stuff is on the right side. But honestly, fluorine is too reactive. And so when fluorine undergoes this reaction, the delta H is something on the order of minus 431 kilojoules per mole. Basically, you try to do this reaction with fluorine and it's just going to blow up. It's a lot of energy. And so pretty much that eliminates fluorine. It happens, but it's not synthetically useful. You're not going to be able to go into the lab and control this thing, and so we don't even consider it. And then for iodine, what we find is, and so really what our thing is, we have more reactive on the left side, and we have less reactive on the right side. And so actually what we find with iodine is delta H is equal to positive 55 kilojoules per mole. And so that's actually an endothermic reaction, and so at room temperature, is anything going to happen unless we heat it up and put energy in? Yeah, and so at room temperature, that doesn't even happen either because it's not reactive. And so what we find is kind of like the what is it, like the three Goldilocks, thank you. It's like Goldilocks and the three bears. This is too hot and this is too cold. But what we have right in the middle is chlorine and bromine, and so that's the sweet spot. So that's what we're going to react in this radical chain mechanism is chlorine and bromine. And so just for your info, the energies here are minus 104 kilojoules per mole and minus 33 kilojoules per mole, which are much more reasonable numbers to work with. All right, so interestingly enough, we do see regioselectivity in our reactions. And like I've been saying, it's dependent on our CH bond. We want to look for the stronger or weaker CH bond. And so when we talk about regioselectivity, what we could do is we could imagine reacting propane. Now, propane's got two types of carbons, right? It's got a primary carbon and a secondary carbon. And so we know that we're going to have to, in our mechanism, form a radical in either the primary position or the secondary position. Which is going to be more stable? Secondary. And so which product do you think forms most? That one, right? The one that goes through that more stable secondary radical. And so what we see is when we react something like propane with bromine, well, first off, nothing happens until we hit this thing with light, right? So we've got to shine a lamp on this thing. Ultimately, what we'll see is regioselectivity. So we can have this product, or we can have this product. What we see is the regioselectivity is about 97% for the secondary and about 3% for the primary. And so with the bromine, you get really, really good regioselectivity. you do this reaction with chlorine, what you see is right around 40% selectivity versus 60% selectivity. And honestly, the thermodynamic reasons for this are really, really cool, and we're just not going to have time to talk about it, and I'm so sorry. But maybe later on in the semester we can come back and revisit this. We just need to keep moving on for today. But the thing to keep, or just to remember from this, is that we do see regioselectivity. It does favor the secondary over the primary. With bromine, it's awesome. We get great regioselectivity. With chlorine, it's not really good. We end up seeing often multiple products, and not only multiple products, but multiple products in significant amounts, such as this 40% minor product. All right, so then finally, we can even show this on a little graph, so we can say that a primary versus a secondary, a tertiary versus a secondary versus a primary carbon in terms of regioselectivity. So if we have bromine and chlorine here, the bromine selectivity is about 1600 to 80 to 1, which is pretty solid. The chlorine selectivity is 5 to 4 to 1, like that. And so you can see it's just not nearly as good as bromine is. So that is sad. Okay, so then finally we want to talk about stereoselectivity. So we've said that radicals, in terms of hybridization, what did we say?
We said the sp2, sp were not.
Yeah, they're kind of in the middle, and so in terms of stereochemistry, they're very sp2-like, and then they're close enough to planar that we can pretty much just consider them planar. And so that means that there's some stereochemical implications. So for one thing, if we have this reaction going on, all right, so we know that we have a secondary carbon and a primary carbon. So secondary is going to be more reactive, and so if I ask you for the major product, we'll draw that secondary. But we know we're going through a radical that is sp2-like and so is planar, and because it is planar, that bromine, guess where it can attack from? Has it got two possibilities? Yeah, if it's a planar-like radical, it can attack from the front, it can attack from the back, and so what we end up seeing is a product from this reaction where the bromine has attacked from the front and the product where the bromine has attacked from the back. And so these are a pair of enantiomers, and so if we did this reaction, we would have started with, let's see, is the starting material optically active? No, definitely not. Are the products optically active?
Yes.
Yeah, but if you have them all in a flask after the reaction's undergone and we put this thing and do the experiment, do we see optical rotation?
No.
We don't, right? And it's because what we end up with is this racemic mixture of two products, and so that together is not optically active. All right, so that's one aspect of the stereochemistry of these radicals. This other aspect is not something that we've really seen before, and so what we can do is we can start with a product, or starting material, that looks like this. Now, is this starting material optically active? Yeah, sure, it's got a chiral center, and so we have optically active starting material. And so I'm gonna undergo again another reaction with bromine. And so what's the most reactive position here on this molecule? Do we have a tertiary carbon?
Yeah.
We have a tertiary carbon, right? It's right here. And so what we're going to do is we're going to go through some sort of intermediate that is a tertiary carbon like this. But what we've done is essentially, where we have stereochemistry right here, if we turn into this radical, do we still have that stereochemistry? No, it's because now we're going through this planar intermediate. And so what happens is, again, the bromine can attack from the front or the back. And so we have two possibilities. So it could attack from the back to give this, or it could attack from the front to give this. And so our product, is it optically active as a whole?
No.
Yeah, because again, what we've formed is a racemic mixture. And so here's a case where we can actually start with optically active starting material, but because we go through this sp2-like intermediate, we end up with a racemic mixture that is not optically active. And I don't think we've seen that happen well, we might have seen it happen a little with EA reactions where we formed a meso product maybe, but this is pretty nifty. And so this is one case where we're actually taking this specific chiral center, undergoing a reaction, and we're racemizing it, meaning that we're going to end up with a mixture over here, a racemic mixture based around that specific chiral center. So stereochemical implications to keep in mind as we go. All right, Roman numeral number 3. Next up, we will talk about allylic halogenation. And this one's pretty nifty. So let's think about a starting material. Let's pick out our strongest. Let's see. All right, so let's start with this material. And so, of course, we've got, I guess, really, due to the symmetry, we've got 3 types of carbons in this reaction. I'm sorry, 3 types of hydrogens, I guess carbons too. And so of these 3 hydrogens, what's going to be the most stable? I'm sorry, what's going to be the easiest to undergo homolytic cleavage to form an allylic radical? Or a radical in general? Yeah, I pretty much gave away the answer in the question, but by undergoing cleavage here, what we're going to end up with is a radical that's next to an alkene. And so we've seen that qualifies, that's an allylic radical. It's very, very stable because we're going to have resonance stabilization. And so what we're going to go through, most likely in this case, is going to be a radical that looks like this, but we're also going to be able to undergo resonance to find that in reality there are 2 possible positions that have radical character, right? All right, so it's going to be 2 reactive, I guess, positions when we have this resonance as possible. All right, so we'll see how this comes into play in a sec. All right, so again, we're going to react with a halogen, and so bromine's pretty much the best at these radical reactions, if you haven't maybe started to pick up on that. And so let's think about what happens if we take this exact starting material and we react it with bromine. What's going to happen?
Like, nothing unless you had light.
Well, nothing without light, and furthermore, have we learned a reaction that looks like this? Yeah, we definitely have, right? So the first thing that's going to happen is we're going to undergo this sort of reaction through a halonium-type intermediate. We'll have this plus the enantiomer. And so what this means is that we can't just use Br2 because we're going to do other reactions with Br2. We already know that this is a reactive species. We've covered that last chapter. And so in this case, we can't use Br2. It's just not going to work. The electrophilic addition reaction is more favorable in this case. And so what we use is actually just going to be a new reagent. And so instead of using Br2, what we're going to use is NBS. And so NBS stands for N-bromo-succinimide. All right, so NBS, N-bromo-succinimide. So what N-bromo-succinimide looks like is going to be a ring with some carbonyls and nitrogen. I will get this right. It looks like this. So we've got carbonyls up top and the bottom. And so what we have is typically we're not used to seeing something like a nitrogen-bromine bond, but that's in fact what we have in this case. It's a nitrogen-bromine bond. And so what happens is that when we hit NBS with some light, we undergo homolytic cleavage. And so this is a fantastic way for us to generate, I guess, not only this radical, but more importantly, our bromine radical. And so this way, we're not going to undergo an electrophilic addition reaction because we don't have Br2 in our reaction. So that eliminates that pathway. And so we're able to generate our radical just like this. And so what you'll also see in CLS doesn't roll off the tongue as much, but you can also use N-chloro-succinimide, and that'll do the same thing. It's the same structure except with a chlorine instead of a bromine, and so it's a way that we can generate our radicals there. So let's see our mechanism for this reaction. All right, so we've already seen our initiation step, right? So our initiation is up here. So really what we just want to talk about is our propagation step. And so in our propagation step, we're going to have some starting material. So we'll use this starting material right here. And so in this starting material, we know we're going to have a tertiary allylic position right here. So this radical is incredibly stable, right? It's tertiary, it's next to an alkene. It couldn't get much better than that. So we have our bromine radical that we've generated. And so what we will do is we will form our new radical, our new allylic radical, which will look something like this. And of course, we've also generated some HBr, which actually is going to come into play in a second, and we'll see how. All right, so of course, what we've really got is a resonance structure, which can be described like this. And so what we find is that there are actually going to be two possible radical reactivity spots on our product. Now, which do you think is more stable? What's the better resonance structure, the one on the left or the one on the right? It's the one on the left, right, because it's tertiary, and so certainly we'll probably expect to see more of that product form, but this isn't that unstable. While it is primary, it's resonance stabilized, and that's ultimately a good thing. And so over here, on its own, doing its own thing, what we have is that our HBr will react with our NBS, or another molecule of our NBS, and so that's going to generate Br2, which we'll see is important. So we have two products, or two intermediates. We have our radical intermediate, we have our HBr intermediate, which reacts with some NBS. Don't worry about mechanism, and then we form some Br2. So what we see, we have Br2 here. So ultimately, what we're going to be able to do is take our radical, to undergo a fishhook mechanism and snap one of our bromines to that radical, just like we really did in the last structure. All right, so we're going to have this as a possibility to form, and of course we'll also have addition at the primary radical, and so that will give us this product as well, plus Br. All right, so which would be the major product? Yeah, it'd be the one on the left because it's gone through the more stable radical, and so we'd have a minor product over here that would result from the primary. And so I might ask you on an exam, give me all possible products from an allylic halogenation that you might expect, and so you'd have to consider what are all the radical-like positions that we have once we've undergone our initial step. All right, so as an example of that, let's say we have this starting material. And so in this starting material, we see there is an alkene, and so what we want to do is we want to look for an alkene that is pretty much, or a CH bond that is next to that alkene. And sure, in fact, what we've got is that CH bond right there that is next to the alkene. So what we're basically going to end up with is a reactive spot here. Where else are we going to have a reactive spot? Yeah, so on this top carbon, right? Because once we have a radical here, we know we can undergo resonance to show a radical at that position. And so what we've got to do is consider all of the possible reactive positions. So if we do so, what we're going to find is that we enter that primary position, we can form this product. Remember, we're going to have that double bond move, just like in the example I've shown above, where it's moved over to the other side. And we can also show addition to that secondary position. But is that going to form a new chiral center? If we put a bromine right here, would that be a chiral center? Yeah, absolutely. And so now we've also got to consider the stereochemistry. So we've got a bromine that could be on the front face, or we could have a bromine that adds to the back face. And so really, we've got three possible products. What would be the major products? Yeah, so these would be our major products because they've resulted from the formation of a secondary radical, and so this would be our minor product. And again, I think it would be fair for me to expect you to come up with all of the products from a radical type reaction such as this. Okay. Roman numeral number 3. All right. I really want to get to our interesting stuff. Is there a question? Yeah, of course. That's what I said. All right, so Roman numeral number 4. Radical addition of HBr. And this one's actually pretty neat here because we've seen HBr react before, right? So what's going to happen in this reaction? That's an EA reaction, right? We're going to undergo a Markovnikov addition. And so what we would end up with would be this product right here. That's just an EA reaction. We've seen that before. But this is going to be another interesting example of when we can put a little thought into the process here and maybe have 2 different products that can form. And so instead of doing the reaction with just HBr, what we can do is have the same starting material with HBr, and now we're going to have this thing that has 2 oxygens next to each other. What kind of functional group is that? That is a peroxide, right? And so peroxides are those things. It's the reason we tell you not to distill down to a dry pot. It's because you can have some peroxides in there, and those can go boom sometimes. So peroxides are pretty unstable things, and so basically what they're able to do is to be a radical generator. And while we see the Markovnikov addition up here, why would I be making this point if we didn't end up seeing a different product? What product do you think we see in this case? It's not Markovnikov, and in fact it is. It is anti-Markovnikov. So all we've got to do is add some peroxides in there, and we can get the anti-Markovnikov addition of an acid. Now sadly, I have to say that HBr is the only thing that works. Yeah. No HCl, no HF, no HI. It's just how it is, thermodynamic reasons. Sometimes reactions are just uphill, and that's how it is. So HBr is going to be the only thing that works here. The way that this works is, again, we're going to have a chain mechanism, and so for our initiation step, what we'll do is we'll take our peroxide, we'll hit it with some light. So we split these apart to form 2 new radicals. So we're going to have 2 radicals that look like this. All right, so now we've generated some radicals using our light, and so from there what we can do is go on. And what happens is our new radical here, make sure I have this right. It's actually the first time I've taught this too. All right, so what we're going to do is then undergo a reaction with our HBr that is in our pot. And so ultimately what we've done is we've been able to generate an alcohol plus a bromine radical, just like that. So now this is our initiation step. We've formed our bromine radical, and from there, what we're able to do is basically, if we have our starting material, sure, let's see. So let's use a starting material that looks like, well actually, why wouldn't we use the one above? All right, so let's use the one above. And so we're gonna have 2 possibilities. All right, so we've got this starting material, and we're gonna draw out 2 possibilities here. All right, so we've got bromine in both of these reactions, so we'll have our Br radical here, and then we're going to have our Br radical here. What we're going to do is we're going to react with the pi bond. All right, so it reacts with the pi bond. So what that has or what we're going to see is that there's 2 possibilities. So we can react in this fashion, or we can react in this fashion. And so essentially what we're going to end up is with 2 different intermediates, right? We can put the bromine on the tertiary or the primary. So in the left case, what we've done is we've added it to the primary, which means we end up with a radical here. In the second case, what we've done is we've added it to the tertiary, which means we end up with a radical there. And so what's the more stable radical? Yeah, it's a tertiary versus a primary, right? And so now we're seeing why we get that anti-Markovnikov regioselectivity. It's because we go through this intermediate where when we add and we just want to consider what's the most stable radical. So clearly, this is going to be the most stable radical. And then from there, what can happen is we can react with another molecule of HBr in a termination step, like this. So we end up with, by far, our major product, this anti-Markovnikov addition product. Does that make sense? It's pretty straightforward, right? We're going to go through the more stable radical, and so the product that results is the one that goes through the more stable intermediate. All right. That was because we have a tertiary versus a primary. That's it. We did it. We're there. That is radicals. We've gotten through it in a day. There's 3 reactions. I've actually got the homework written already. I'll just get that posted. There's lots of good examples for you to work through there. And then in the last 5 minutes, you ready for this? Fun facts. Huh? Yeah? All right, so some fun facts about radicals. Number 1, we're going to talk about CFCs. Who's heard of CFCs? Yep, and so when we talk about CFCs, those are chlorofluorocarbons. And so what we have is, that's what we used to use these chemicals for refrigerants. And so an example of a chlorofluorocarbon is exactly what it sounds like. It's a carbon with chlorine and fluorine. And so you can imagine a world where you have food, and you keep your food in a refrigerator. And so over time, these refrigerators are pumping out our CFCs. And so what we have is, very sadly, CFCs being vented off to the atmosphere. And of course, there's Mr. Sun over here. So why wouldn't I use yellow? I have no idea. Okay. So there's Mr. Sun. And so what we have is we have fluorine and carbon and fluorine. And unfortunately, what is Mr. Sun creating? Uh-oh, right? And so what occurs is that we're going to undergo homolytic cleavage with one of the carbon-chlorine bonds, such that we end up with this structure plus this structure. And so very, very sadly, anytime that we have a chlorine radical plus, what's it reacting with up there? Ozone. Uh-oh. And so ultimately what occurs is we're going to form a lot of different things, a lot of interesting pathways. One of these is going to be this. And so essentially, all of these CFCs are able to go up there and create radical. And so the thing is, the reaction doesn't stop, right? It's not going to be a one-to-one, because we've created another radical here, which can go on and do other radical things with ozone. And so ultimately, the result is a hole in the ozone layer. And so that is very sad. But there is good news. We figured that out. Some scientists back like in the 50s or 60s really got to work on this. And so now we use HFCs, which are hydrofluorocarbons. And so essentially they have similar properties, but we don't have that chlorine. And so these are much better. The bad news about those, though, is that they're implicated in global warming. So you can't win. All right. All right, so that's one. We're down to 2 minutes. Okay, so next up, I just want to talk about oxygen. And so oxygen is actually really interesting because oxygen, you can't live with it. You can't live without it. And so let's talk about the pros and cons. All right, so the pros. Aerobic respiration. I don't know about you guys. I'm big on it. I think it's a good thing. The cons. Kills you. And so honestly, the relationship with oxygen is incredibly interesting because it is necessary for life, but it does also slowly kill you. It is implicated in so many things like cancer and diseases, and is one of the biggest things implicated in aging. Why do we age? There's a good chance that it's the oxygen that is basically you're bringing into you welcome it in, and it's a Trojan horse. It then destroys you from the inside. And so why is that? Interestingly enough, when we draw a structure for oxygen, maybe a more accurate picture of oxygen is this right here. And so this is actually it's a more stable form of oxygen than the double bond. It's for molecular orbital reasons. Remember the stuff we skipped over a lot of? It's that stuff. And so basically, O2 exists as a radical, and so when it comes into your body, most of it doesn't do bad things, but some of it turns into random radicals, hydroxide radical, O2 minus radical, and so it does DNA damage. It also does the oxidation of lots of fatty acids and amino acids, which can deactivate your enzymes and pretty much destroy you from the inside. And so to avoid that, your body takes advantage of antioxidants, right? And so that's why you take your vitamin C and your vitamin E, and those are all sort of involved in that pathway. And so your body recognizes that oxygen sucks. And so what it does is it basically has pathways to deal with all these oxygen radical species and to shut them down. So another interesting thing about radicals. Yeah.